Great. Okay, so thank you everyone to be here, and I'm very happy to present the work of the Earth Initiative. So I'm Claire Rubin, I'm PhD student at the Max Planck Institute for Biogeochemistry, and this work is a collaboration with Vitus, Prazon, Lazaro, Jose, Seyan, Christian, Melanie, Mark, Nuno, Marcus, and even other members of the team. On this image, you can see that in 2019 and 2018, the spring satellite images are pretty similar in Greece, but when we moved to the summer of 18, the heat wave had a strong impact on the vegetation, and it's visible from satellite data. Here we are focused on predicting hazard forecast. So what we say is that we have observation, satellite data observation, and weather forecasts who are given by other team, and what we want is to model the environmental relationship between weather and vegetation, and forecast the impact of this extreme event and weather to support impact forecast and early warning system to support decision making by stakeholders. Okay, this one I will skip it. The idea behind that is to support anticipatory action and reduce the humanitarian crisis caused by extreme events by supporting, for instance, drought-resistant seed in case of drought prediction. For that, we use Sentinel-2 data. So from ESA, so we really work at very high resolution at 10 meters with a temporal resolution of 5 days. And we have X years of data and 13 bands from visible to infrared. And what we do is that we say, okay, we will take satellite data from past the last satellite data that we have, meteorological variables and elevation. And what we want is to predict how the vegetation will evolve in the future. And for that, we use machine learning model. We do that across a lot of different land cover and across different biomes. And the idea is that we have this context information, we have this previous historical Sentinel-2, we have this previous historical weather data and historical map, and we want to predict, so up to 10 days, 3 months, even more if we can. And so far we use historical weather data, so error fiber analysis, and we use them to guide the prediction. So in the future, we predict how the vegetation will evolve following what are the forecast weather. What we would like is to use a future weather scenario from ECMWF, seasonal forecast ensemble, to use the actual future weather. And with our model, we are able to predict at very high resolution. So on the left, you can see it's a sample somewhere in West Africa. And our target is NDVI, so it's the greenness of the vegetation. And you can see that on the target, we have a river in the middle. And this river clearly influences the vegetation around, because we can see that it's very red. And it's become more red across time, so more greenness. And what we can see is that we are able to predict that. We are able to predict at very high resolution how it will evolve in time and space. On the bottom, it's the prediction, the error. I mean, it's a NDVI prediction for each time step. And in green, you have the error. So we can see that our prediction is actually very close of the actual NDVI forecasting. And we use that for worst case. We want to use that for worst case scenario, for instance. In this case, we change the weather. So on the left, it goes from almost no precipitation to a lot of precipitation. And from top to bottom, from normal weather to warm weather. And this was the one, sorry. And so what you can see that across time our prediction really show how the different weather will impact differently the vegetation, and so we can have this ensemble scenario depending of the weather. So to do that, we developed several datasets. The first one was SNet21 in Europe. Then we improved it with a cloud masking and more test sets to have something which is much more robust now. And we have another dataset in Africa because we want to focus more on drought. And the last one is it will be published soon in the Deep Extreme project, and it's focused on compound event when there is drought plus heat waves. So all these datasets are either available openly available, or will be available very soon. And we developed several models. So some of them are were the state of the art a few years ago, such as convalescent, and now we are focused on more the last recent model on transformers. We just have been, our last model have been accepted in the machine learning conference, where we show that this new model who uses transformers is able to outperform all the previous models. And a second point that we are focused on, it's on robustness. So we would like to ensure that subgroup of different biomes and land cover are accurately predicted, including during extreme events. So we have this problem that we have a lot of subgroups and they're not all, we want to ensure that when we have different land cover and there's different environmental processes, we are able to predict all of them and not only the more dominant one, and to actually learn these underlying processes. For that, we really have a lot of work on this robustness to do, especially with out of domain. Like, how can we deal with unprecedented extreme event and climate? Because we have a lot of data in the past, but we have no data in the future, and we need to deal with that. And for that, since it's very hard to deal with this lack of data, we are also working on space. So if we is a model able to predict in unseen region, in unseen land cover? And we did a small exercise who just have been accepted in a machine learning for remote sensing workshop, where we train on all over the world and we remove Africa and we see how our model is able to perform in Africa. It's an ongoing work to because it's depend of a lot of, we need to disentangle the effect of different biomes and different land cover. But so for the outlook of all this work, we have a lot of progress in different way. We have the machine learning improvement. We would like to develop new models who take better into account the spatial temporal dependencies and develop a foundation model for climate risk early warning. But we also need to work on this robustness and evaluation method to be sure that our model is accurate and can actually be used. And we are working on how long we can predict. So far, we were predict at very close scale, few months, but we are dependent of the quality of the weather forecast, of course. And so we want to see how far we can predict and have the what if scenario, since we know that extreme event will increase, how we can predict what happens if a drought happens in 10 years and see how it impacts the vegetation. And collaborate to move toward real-world applied studies. So far, we are working with the Red Cross to try to develop pastoral drought anticipation action, because in situations there is a lot of drought and strong impact on the population. This drought have a strong impact on the population. It's also interesting because so far we don't use human management information. We don't have them at global scale. So we also have this limitation. So we are working on both in application where human land management is not too strong, and on how to improve the use of that human land management. Thank you very much. It's the end of the presentation. I hope it wasn't too long. Do you have a question?